is now on, and we can proceed. Today I'm glad to introduce you to Tolga Çukur from Bilkent University. Dr. Çukur received his BS degree from Bilkent University in 2003 and his PhD degree from Stanford University in 2009, both in electrical engineering. He was a postdoctoral fellow at Hernandez Neuroscience Institute at University of California, Berkeley till 2013, and currently he is an associate professor in the Department of Electrical and Electronics Engineering at the same time at UMRA and Neuroscience program at Bilkent University. His lab develops computational imaging methods for understanding the anatomy and function of biological systems in normal and disease states. He is the recipient of TÜBİTAK Career Award in 2015, TÜBİTAK GİBİP Outstanding Young Scientist Award in 2015 also, and Bagip Young Scientist Award in 2017, and also IEEE Turkey Research Encouragement Award in 2017. He's also a Science Heroes Association Young Scientist of the Year Award recipient in 2018, and he's a senior member of IEEE. So I'd like to welcome our speaker again. Thank you very much for coming. So I leave the stage for you.
So I'd like to thank the organizers for the nice invitation before I start. So the title of my talk, I assume it will be mostly self-explanatory. What I'll try to do is give you a brief survey of technical development efforts on the MRI side that my lab has been pursuing in the recent years. Just to give you a brief idea of where I'm coming from, my lab is part of the Brain Research Center in Bilkent, which was recently upgraded to a larger building. We have research-dedicated labs on MRI, EEG, and also animal experiments. We have a collection of 100 researchers and maybe over 20 faculty these days, and they come from a broad range of disciplines. So the work that we do is mostly interdisciplinary because of the biomedical aspect of the research. Now today I'm not going to talk about the applications, but more so the technology developments. So we have three modalities that we are pursuing in the Brain Research Center, and with most of them, apart from EEG, we are pursuing both hardware developments, novel acquisition methods, image reconstruction, and finally statistical modeling of the data that has been acquired. Today I'll mostly talk about data acquisition and image reconstruction for MRI in particular. Okay? And a lot of the research actually is done on MRI, so you may be wondering why we want to work with this modality so much. Now, in modern times, there are a range of imaging modalities that are available to the clinician, from X-ray to MRI, ultrasound, nuclear medicine. You might be wondering why it is easier and more interesting to work on some of these than others from a radiologist's perspective. And for that, the question that I ask myself, and I think it's a good one, is to figure out what makes a good imaging system. So of course, there are many things like sensitivity, versatility, and the harm that it delivers to the patient, but the two that I'm going to focus on this talk is the first one, resolution. Because everyone likes to see fine-grained texture in the images as opposed to blurry images, which will make it hard to distinguish tissues. And the second one is, of course, contrast. Okay. You want very sharp contrast to distinguish the target tissue of interest from the background. And if you have very low contrast, it will be harder to spot that difference. And from this perspective, MRI gives you a very nice trade-off between contrast and resolution, I would say, among the available modalities. On top of that, it's completely non-invasive because it does not involve ionizing radiation like CT or X-ray, so you don't get exposed to that. It can image arbitrary geometries across the human body without having to slice through anything. And most importantly and uniquely, it has a broad range of contrasts that you can acquire, unlike CT or X-ray, which is a single dominant contrast that is collected. So you can image the human body, different sites under different contrasts. You can look at anatomy. You can emphasize vascular structures, and this is the flexible contrast component. So you can comprehensively assess both the morphology and function of tissues, especially in neuroimaging experiments and neurological scans. MRI is the predominantly chosen modality even in the clinic, apart from research. But there is one caveat. That's MRI is, although it has very flexible contrast, it has limited spatial or temporal resolution. It relates to the way data is acquired in this modality. Okay, so you either need to sacrifice this, or if you're in the clinic, okay, using standard protocols, if the scan takes too long, okay, although the radiologist asks for some range of distinct contrast to be collected, the technician will decide it's time to end the scan, only collect a subset of those, and the radiologist will have to do the best that they can with the data that's available from the patient. And this is a big problem. Actually, this compromise is continually made in the clinic without you having to notice it, because there's about a cap between somewhere between 30 to 40 minutes that you can spend on each patient. Okay? If it takes longer, no luck. You have to do with what you have. So we are trying to solve this problem, and this is related to the fact that MRI is slow. So to understand what we are imaging, okay, we are exploiting a phenomenon called nuclear magnetic resonance. When you have any atom with an odd number of protons or neutrons, it has magnetic spin under large static magnetic fields. And this magnetic moment is what we are imaging in MRI. Of course, there are many atoms that would exhibit this phenomenon, but water contains hydrogen and is widely abundant in biological tissue. So most scanners in the clinic focus on the hydrogen nuclei. So we are imaging hydrogen splits. Now, when you lie in an MRI scanner, there is a really strong magnetic field that is studied 1.5 to 3T, depending on the model. And then all the spins tend to align themselves with the direction of that static magnetic field. This means that you won't be able to distinguish a spin that is in some part of the body from another. So you need another encoding mechanism. So we don't have pixels like in a CCD camera that we can use to do spatial encoding. What is done in MRI commonly is you apply magnetic field gradients, linearly changing magnetic fields across, for instance, in this case, the x-axis. And it creates a systematic variation in the direction of the spin. So the phase of the spin is altered with respect to spatial coordinate. You can do the same thing on the y-axis and the z-axis. And what you do at the end, you use a radio frequency coil to capture the magnetic field emitted by the collection of these spins, the entire volume. So when you do that, this is the signal that you receive. M is the spatial spin distribution, and I'm sure many of you notice what this is. This is nothing but the Fourier transformation of the spin distribution. Okay, so in MRI, we do Fourier encoding to capture spatial information. It's called K-space as opposed to Fourier domain in the MR literature for some reason. And then, according to Nyquist sampling criteria, you want to avoid aliasing. You capture a discrete set of samples in the spatial frequency domain. The reconstruction is really simple. If you have corrected the correct number and density of samples, you do a Fourier transformation, and then you recollect, in this case, a brain image. Okay. So this is the main idea. But there's an issue. The higher the spatial resolution that you want, okay, you basically need to increase your coverage in the Fourier domain. So you need to extend to broader spatial frequencies, higher. And then this means you get many more samples to acquire in this broader domain. And that's why the scan time increases when you try to go for higher resolution. Okay. What is the solution to this problem? There's not much that you can do. And there are some tricks that you can play on the pulse sequence side and others, but they also introduce some trade-offs. They change the intrinsic contrast of the image. So what is most commonly done is you choose to undersample the acquisitions. We violate the Nyquist rate, and as a result, we are going to get aliasing artifacts, but unlike what you may be used to seeing aliasing artifacts in frequency domain, here we are sampling in Fourier domain, therefore the aliasing occurs in image domain. So you get replicas of the brain overlapping onto each other, and this makes it impossible to look at the tissue, and you can't really see what is underneath this. You can, of course, make it slightly of different shape by changing the way that you sample K-space, but you cannot get rid of it. So our goal in MRI is to accelerate the scans using undersampling. We now have artifacts. We want to solve an inverse problem. The goal is take these original subsample data, okay, with aliasing artifacts if you did a linear reconstruction, and somehow recover this higher quality image that is mostly free of artifacts. So how do we solve this inverse problem? There are a bunch of ways, but the one that has been most dominant in the MRI community in the past decade, I would say, is the idea of compressed sensing. Compressed sensing is very broadly applied to many domains of signal processing, but it also applies very nicely to MRI because MR images are a subclass of natural images which are known to exhibit the property of sparsity or compressibility. The notion is you take some non-linear transformation of the data, okay, and in your new domain, although you started with n pixels to represent the image, you now can get away with much fewer coefficients that are non-zero. Okay? And this is a lossless transformation, so you actually did lossless compression of the data if this idea works. Okay? And I'm not going to go into the technical details, but there are a bunch of other conditions that we need to satisfy. You want to do random sampling according to CS theory. The idea is you want to make the Aliasing artifacts not look like biological tissue, but more like white noise-ish patterns, so that they are easier to distinguish than actual tissue once you start segregating them apart. And if you use then a nonlinear reconstruction that enforces the sparsity in the transform domain, then you can actually get good reconstructions even though you subsample your acquisition. Now this can also be viewed as a Bayesian framework where you have prior knowledge about the image, how it's distributed, and you have some experimental evidence about what you're trying to recover, so you weigh them against each other. If you find the correct weighing, then you should be able to recover a decent image, at least, if not ideal. And there are many demonstrated uses. I'm not sure if it's visible on the slide, but you can see that by applying this strategy, you can go to acceleration factors, these days much beyond 4, but this is somewhat of an older slide. And without increasing scan time, you can increase the details which you can see in the image itself. So it works overall. So it has been applied to a broad range of applications. What I want to talk about today is its application to what we call multiple acquisition MRI or multi-contrast MRI. Now, I think partly because this problem is a little bit more challenging, people have skipped the application of compressed sensing to this problem, but in the clinic, when a radiologist asks you to get a brain scan, they never collect one single contrast. They don't collect, for example, the image at the center and then stop. Because if you compare these are of the exact same anatomy, but the tissues appear at different signal levels. The reason for this is the contrast has been manipulated to look at, to make it most sensitive to the difference between gray matter and white matter in this case, to look at the difference between fluids in the brain and regular tissue, and in this case just the proton density that gives you an idea of the myelination that exists in the brain. So all of these contain non-overlapping and important information for diagnosing the disease. And what is done currently, if you apply compressed sensing to this problem, is to take each image and consider the problem, the inverse problem, separately for each of them. So you acquire the data for one of them, you run an independent recon, you obtain this image, you move on to the next one, as if they have nothing in common. But from an information theoretic perspective, you know that they share the same underlying anatomy, so there should be correlated information between them. So one of the first things that we did is we devised what we call a joint or a tensor reconstruction to jointly process the data and make use of the shared information between these contrasts to get a better reconstruction, better recovery at the end. I call it a tensor because there are 3 spatial dimensions. There is something that I skipped. We collect data not using a single channel radio frequency coil in MRI, but a phase array coil that has, in modern scanners, about 32 channels. And on top of that, you add the acquisition dimension, in this case 3. So it becomes, it's easier to represent this data in a tensor format. This is partly the reason why people don't like to touch this problem. Often you get a very complex optimization problem when you try to solve this. These terms above, this is in partly Lagrangian form with the data consistency constraint at the bottom. This basically respects the experimental evidence that we collected. The ones above try to enforce the sparsity of the image in different domains. Now, once you are collecting images of different contrasts, you cannot get away with a single term. You need to use both joint sparsity terms that try to enhance the recovery of shared features across different contrasts due to anatomy. And you also need to respect the individual unique differences in each contrast, because some features like lesions or tumors may only come up in one of the contrasts. If you only enforce joint sparsity, you will lose it. So you want to also introduce these individual sparsity terms. Now, the weighing of prior against data consistency is hard because there are so many free parameters, but if you have a strategy to pick them properly, then you can get good reconstructions. This is one example. Okay, the images are not, differences cannot be seen partly due to the projector, partly because of my slide probably. But if you look at the error maps at the bottom here, this is our reconstruction. These are different types of independent reconstructions. You see that the errors are reduced, especially at high spatial frequency transition. So it seems to help to include multiple contrasts, especially for the regions that are mostly undersampled in our data. And this is, I hope, somewhat of a clearer example. In this case, this is our approach. This is an independent reconstruction. And we did this experiment to show what happens if you only enforce individual sparsity of the contrasts, and what happens if you only enforce joint sparsity. So in those two cases, you lose some of your power to solve the inverse problem. It results in residual aliasing effects, which are cleared much better in the joint reconstruction. I apologize for the ways the images look, but not much that I can do to fix it now. So that's one component. The second component that we started looking at once we had this joint reconstruction framework is how you pick the samples to acquire across these contrasts. In compressed sensing theory, you're supposed to pick them entirely randomly. So if this is case-based, you just you need to use a uniform density function and then do a random selection to abide by the constraints of CS theory. But with natural images and MR images in particular, in the transform domain, this leads to very low levels of aliasing interference in different wavelet subbands. Now, if you think about the problem of CS recovery as selecting a threshold that separates the tissue signals from interference, it's impossible to select a common threshold that will denoise all of the bands at the same time, so you end up with kind of poor reconstructions. In MRI, what we do is we deviate from the strict theoretical requirements and we do variable density sampling, so get more samples towards lower spatial frequencies and then gradually diminish it towards high spatial frequencies, because this is the way energy is actually distributed in natural images. So we respect the energy distribution. Then you get uniform interference in different wavelet bands, so you can pick a threshold that will actually give a much nicer reconstruction overall. So this is the standard method. But the way this is again applied is, since you think of the reconstruction problem separately, then the data acquisition is also thought independently. You pick a different random mask for each acquisition. But if you were actually, forget about this problem, if you were collecting the same image 3 times, you would not want to hit the exact same spatial frequency points. You would want to diversify a little bit so that you have broader coverage. These are not the same image, but the idea still applies here. So what we did was to come up with a statistically segregated sampling framework. We basically take the joint probability distribution function of n separate acquisitions. We do a conditional decomposition of it, just probability theory. And then we have some constraints that ensure that the shape of the PDF does not change too much between the acquisitions. But the idea is, if a sample has been collected previously, so we do a sequential design here, we reduce its PDF, the probability value, by some much, and then boost it up in points that are not sampled before. It's really a simple idea. You just need to be careful to abide by the axioms of probability theory, so it doesn't blow up beyond one. So this shows the schematic. If you look at the masks that are generated in sequence, not looking at them won't make you tell the differences, but if you look at the PDFs, you see the small granular changes that we enforce on the PDF to ensure that they are segregated from each other. As I said, you cannot see it from the masks, but if you do a comparison between the regular method, just select 4 different initializations, instances of random masks, versus our method, when you combine the total coverage, you can get up to 20 or more % improvement in the FLIR domain. And this means you have more information at high spatial frequencies than before. Okay. And this translates very nicely into quality in the final reconstructions. Again, maybe it's not seen, but there is residual noise and everything here. Some features are not seen clearly, but only seen here because of improved recovery of high spatial frequencies. That's the second part. And the third part is how we pick the various parameters that weigh our priors against the experimental evidence. That's the most critical part. This is not in Lagrangian form, but in constraint optimization form. Here we have sparse terms, and we put bounds on them, denoted with these epsilon parameters. Now, if you go to a clinician, okay, and tell them, for each subject, for each type of contrast that you want to acquire, you need to tune these just right so that the image looks good. Okay? Because if you don't tune them right, you can remove image features if you enforce too much sparsity. If you use too low parameters, you won't do any denoising at all. The aliasing will remain. So this needs to be tuned in just right. Okay? But there are 30 or so parameters here for the joint reconstruction problem, and no technician has the time to deal with that. They'll just use it with whatever default parameters that you gave them, which means poor quality reconstruction, so no one will be interested in using your technique in the clinic. So to pick each of these parameters, we first use the decomposition approach. You take the complex optimization problem and decompose it atomically into smaller sub-projections. These are for L1 norm-based penalties. This is for total variation-based penalties that we have. So this is a generalization of the complex projections onto sets idea, where we have more than one projections, and they may not be necessarily convex, but we have still mild convergence properties in this case. I'm going to talk more about how we do this, the parameter selection. So if these are, this is the vector that you start off with, this is the wavelength coefficients of the image that you have at that point. You want to project it onto an L1 ball of a certain size when you do this L1 regularization to cap off its L1 norm and enforce sparsity. But the question is how to pick the size of this L1 ball. Okay. We take a heuristic approach. We construct what is known as the epigraph set of the L1 norm function. Okay. And the level set, which is the boundary of the epigraph, is the important part for us. So basically, the z-axis represents the L1 norm of the image, and the image itself is in the transverse plane. So when you plot the region where the L1 norm equals the image value, so the z-axis equals the L1 norm of the image, then you get the level set. Okay? And we reason that if you start off with omega, you should project the data onto the closest point on the level set. This gives you the smallest deviation away from the actual data for the greatest L1 minimization that you can obtain. So this has been shown to work heuristically well in practice. So this is how we determine the L1 ball size. We have a similar approach for TV, but in this case there is no closed form solution. So we cannot do soft thresholding, but we need to do a conjugate gradient-based method to iteratively project onto the TV level set. And these are the results of the self-tuning reconstruction. This is the one in the middle. There are some alternative approaches that people have tried based on Stein's unbiased risk estimation. So you have online estimates of reconstruction error, and you do a line search across your parameter space to pick the best parameter. But it's computationally expensive and it doesn't work as well. In our case, we can recover the underlying structure much better. What's important is this brute force approach here. Here we assume that we have an oracle reconstruction that has access to the ideal reference image, and it just does a search across the entire parameter space, just tests all possible combinations and figures out the best one. Our reconstruction, in both quantitative terms and visually, is very close to that. So this is where you want to get your reconstruction. It works quite well in practice. Now the last part that I kind of skipped is the idea of a sparsifying transform. Okay, we assume that they might be sparse in wavelength domain, total variation domain. People use DCT and other transforms, but there is no single known transformation that is optimal for each contrast, for each patient. And even if you scan the exact same patient on multiple different days or scanners, the data properties would change, so how much you can accelerate with a specific transformation might vary. And we don't we can't do much if we don't exercise dictionary learning for the specific data that we have at hand. Wavelet is not tailored to MRI data in particular. So then we reverted to, due to the success of convolutional neural networks in computer vision applications, we reverted to deep learning for feature extraction. The initial idea was to train CNN architecture either on natural images, but maybe possibly on a large collection of MR images. For instance, a sparse autoencoder would learn the domain, even if it's nonlinear, in which data are most compressible. Then we thought that we could take that transformation and embed it in our compressed sensing framework to do the optimization. That seemed like a great idea, and it didn't improve our reconstruction so much. So we said that the network maybe knows how to do the entire process much better than us, so then we skipped onto this. So you take the undersampled earliest images, okay, you give them to the network as input, and you give the reference ideal fully sampled data on the output, and you let the network both learn the features and to do the reconstruction. Okay? Let's not waste time with optimization framework in a Bayesian sense. Just let the network do it. So you need to train this using a lot of data. That's the downside. But then once trained, you can apply it on the testing data to perform the reconstruction, and it works real well. So this is the regular compressed sensing reconstruction. These are three flavors of network-based reconstructions, and this is the ideal reference image. So in terms of structural details, these are very close to the ideal reference, and you see the blurring or loss of some spatial frequency information details in the CS reconstruction, and there is a good 3 to 4 dB difference in peak SNR in most cases. Again, I apologize if you're not seeing the differences between the images, but I can show them afterwards if you're interested. What is interesting is this one has not even seen any MR images. Okay, this is just transfer learning. Basically, we trained it on ImageNet, and it works much better than anything we were able to develop in the last decade with compressed sensing. So there is something to be exploited there. But then our quest was to take this and to apply it to the joint reconstruction framework. So the previous one is for independent reconstructions. And there are two main frameworks that were previously used. One is reconstruction, so you undersample, and then you try to recover your image. But if you undersample too much, like 50-fold, 100-fold, then you almost will get a blob that looks like a brain-shaped ball, and you will lose all the high spatial frequency information. The other one is called synthesis. Here you actually acquire a fully sampled image of a different contrast, okay? And then you try to predict what the same anatomy would look under a different contrast. Now, this is much better at preserving high spatial frequencies, but it can hallucinate features that are not supposed to be there. If you look at the reference, there's nothing there, but because there was a lesion in the T2 image, it tried to create something there. So this is a big problem because a radiologist looking at this would come up with a misdiagnosis. So we saw that these have different advantages and disadvantages, so we wanted to merge them in the same framework. And this is how we did it. So we call this joint reconstruction and synthesis. You have lightly undersampled source images that are of high quality to begin with, so they can even be fully sampled. But this is just to introduce some flexibility. And then you have heavily undersampled target images that we actually want to reconstruct. Okay. And then you put them together into a generative adversarial network structure. I don't know how many of you are familiar with that, but this is game theoretic approach to neural network training. If you want to think about the generator, you can think of it as the imitator who's trying to create fake diamonds. And then there's a discriminator network that is separate, that is a diamond expert that tries to tell apart the fake ones from the real diamonds. So somehow the inclusion of this discriminator, the expert, makes the generator perform much better than it would if you'd have straight supervised learning. Okay? So that's the main idea behind this. And this is a comparison of a pure reconstructing network versus reconstruction and synthesis network. And these are the actual data with linear reconstruction that we obtain. If you go to 50x, you get, of course, very blurry images. All you have is low spatial frequency information. The reconstruction network, it starts off good, but towards higher acceleration, it starts introducing some realistic looking but fake features. This is one problem with the generative adversarial networks. They create hallucinations, and they look so realistic that we can be mistaken to think there's some problem with the brain there. And the Arrestian approach, which has a constraint due to the source contrast, is immune to this problem. That's the main idea. That was our goal. And this is a demonstration from a patient. Okay. This is a synthesis network. It creates the hallucinations or losses in regions, or it can sometimes miss the tumor because it doesn't have that information available. The reconstruction network loses high spatial frequency information, and our approach gets the best of both worlds, trying to limit the problems with the final image that is recovered. Okay, so those are the components that I wanted to talk about today. Overall, especially the last part of my talk, I think shows us that it's very promising to pursue deep learning in medical imaging and biomedical research, not only for more structured tasks like reconstruction, synthesis, and even segmentation, but they can help with you pick how to collect the data in a better fashion so that the final reconstruction is better. They can help the clinicians with tumor lesion detection, disease gradient, treatment planning, and monitoring. So there are a broad range of applications to be introduced there. And the nice thing about this is, I think when compressed sensing came in about 10 years ago or so, we were thinking it would be limited to a couple of applications, but all of a sudden the entire reconstruction pipeline in the MRI machine almost got replaced by CS. And now we are at the beginning of the DL revolution, and I think within 10 years, most of what radiologists do is going to be done by AI machines, so we might not have some professions available anymore. But the nice thing is they are much better at these tasks than human observers, so the overall quality improvement in healthcare will be worthwhile. And that's the end of my talk, and thank you for listening. And if you have any questions, I'm happy to answer them.
So we have plenty of time for questions.
Ben başlayayım o zaman. Bu ilk deep learning ile ilgili gösterdiğim ilk örnekte Tolga. Undersampled görüntüler ve exact görüntülerle train ediyoruz dedi. Oradaki undersampled görüntüyü, yani orada raw data'yı mı kullanıyorsun, yoksa basit bir immersion yaptıktan sonra o artifact'e çıkan görüntüyü mü kullanıyorsun?
İki türlü de yapılabiliyor. Doğrudan Fourier domaini de verebiliyoruz ama buradaki örnekte simple bir FFT aldıktan sonra image'ı verdik. Yani tamamen image domaininde çalışıyor bu. Ama öteki türlü de çok büyük bir farklılık olmuyor. Tek önemli farklılık bu her CNN stage'inde datanın normalize edilmesi gerekebiliyor eğer case space'de verirsek amplitüdler farklı olduğu için image domainden. O bazen problem çıkartabiliyor. Onun dışında bir sıkıntısı yok ama.
Peki network yapısı olarak burada ne kullandınız?
Bu hiç boyutu azalmayan, aynı boyutu preserve eden bir CNN. Burada convolutional layer var 5 katmanlı. Arada şimdi compressed sensing'i kullanış şeklimizi hatırlarsak bir experimental evidence vardı. Bir de prior'ımız vardı. Burada convolutional network prior'a denk geliyor. Convolutional neural network'ün çıktısına da data consistency uyguluyoruz. Yani orijinalde topladığımız dataları yerine koyuyoruz ki onları değiştirmesin. Ve bunun bu şekilde sanırım yanılmıyorsam 5 cascade var. 5'ten sonrası çok improve etmiyordu, o yüzden orada durduk. Ama yani bunlar açık parametreler tabii. Optimize edilmesi gerekiyor.
Yani sanki daha çok sorun varmış.
Devam edelim. Sonsuza kadar sorabilirim.
Devam.
Bence başkaları da sorsun.
Sanki yok gibi şu an. Devam edebilirsin yarısına.
Şimdi aslında o data fidelity terimini var dedin ya içeride network'in için. Onlar olmadığı zaman bu network'lerin aslında çok fazla sumut alt ettiğini hani görüyoruz inverse problemlerde. Genelde böyle bütün texture'lar falan gidiyor. Ama sizin reconstruction'larınızda o böyle texture tarzı yapılarında kaldığını gördüm ben. Hani onu net söyleyebilir misin?
Onun iki nedeni var. Data consistency koymak daha yüksek çözünürlükte algısı yapıyor. Yani fark ettik yani teorisini bilmiyorum ama bu reconstruction'larda değil de bu GAN, yani Generative Adversarial Network tabanlı olanlarda o adversarial cost function'dan dolayı oluyor. L1 ya da L2 penalty kullanırsak blurry görüntüler çıkıyor. Adversarial cost bunun tamamen daha düzgün çıkmasını sağlıyor. Ya bu da bilinen bir şey computer vision'da en azından. GAN network'leri görüntü sentezlerken ya da natural image oluştururken çok daha yüksek çözünürlükte yapabiliyorlar hallucinated eserlerde. Tamamen onunla ilgili network yapısıyla.
Hocam ne kadar sürüyor acaba bütün training prosesi? Yani muhtemelen birçok deneme yapılıyordur fakat hani,
evet.
Sağlıklı bir denemeye geçtik dediğinizde toplam baştan sona ne kadar sürede
Yani bu network yapısına göre çok değişiyor. Normal deterministic convolutional neural network yapıları ilk başta gösterdiğim architecture'ların training'i birkaç saatlik bir iş. 1000 tane görüntüde yapacaksam diyelim. Bunlar çok kolay train oluyor ama generative adversarial network dediğim yapıların şuradaki training'i bir tane model, yani bir parametre seti için 3-4 gün sürebiliyor. Yani bir makale için gereken tüm analizler 3 ay, 4 ay alabiliyor. Bu tamamen nasıl bir GPU cluster'ın olduğuna bağlı. Ben single GPU'dan bahsediyorum. İşte 10 tanelik bir cluster'ın varsa paralelleştirip çok daha kısa sürede yapabilirsin. Ama training'e ayrılan zaman bu alanda çok o kadar önemsenmiyor çünkü kullanım sırasındaki hızı çok milisaniye, yüzlerce milisaniye mertebesinde olduğu için bir reconstruction yapmak. Klinik açıdan hiçbir sıkıntısı yok o training'i önce yapmak.
Perhaps we can also continue outside when we are drinking our tea and pastry. So we thanks